All right, can everybody hear me? Awesome, awesome. Welcome to my talk, Adventures at HyperScale. Having a good time at NDC so far? All right, I'm gonna start with making a little bit of correction. This is the abstract that I sent him for the talk about a few months ago. Can't remember exactly what it was. It's not entirely accurate anymore. I was looking at the stats, I think, yesterday. It's pretty much changed to this. It's a hefty increase. So before I start, I'm going to tell you a bit who I am. My name is Stefán Jökull. I'm Icelandic. I'm the first employee or full-time employee of Have I Been Pwned, except for Troy. Been an MVP since 2020, mostly developer technologies, and there's a link to my blog. It's been a while since I blogged, but still there anyway. So most of you are probably familiar with Have I Been Pwned. Is anyone that's not familiar with Have I Been Pwned? What it is? 1, 2. All right. Okay, you'll get to know it. First of all, to answer the question, yes, you have. It's a simple answer. I would be very, very surprised if there is anyone in this room that has not had his data breached at one point or another, or has his data leaked with all the multitude of services that we use every day. The service was created by Troy Hunt. He's been a very regular NDC speaker. Unfortunately, he's not here this time. He created it in December 2013, December 4th. And it was a hobby project when he started it. It basically allowed internet users to check if their data had been in a data breach before. And when he launched it, it pretty much contained, I think it was like 3 breaches, the Adobe breach, Stratfor, and one more, maybe LinkedIn, can't remember. It has piled on a lot of features since then. There are breach notifications, so you can go to Have I Been Pwned, you can sign up your email address, and you will be notified if there's a data breach containing your email address in there. And that's completely free for individual users. There are domain searches, so if you have a domain, or if you have a company, you can register the domain, prove ownership of the domain, and you will be sent, like if we load a data breach and there are like 5 of your domain's email addresses in there, you will get to know which email addresses those are. We recently added stealer logs. Unfortunately, people sometimes get malware installed on their machines. The malware can, for example, record every keystroke you make, recording all your credentials. A lot of these stealer logs are, often it's just like a billion lines of username, password, URL, where unfortunately people have had a keylogger installed on their machine and nefarious people have stolen their data. There are enterprise subscribers. These are our sort of biggest users. An example of those is, for example, Mozilla and Firefox. Mozilla Firefox and 1Password, sorry. And we have an API as well. So most of the data that you can fetch on the website itself can be fetched via an API. And one of those APIs is also what we call the Pwned Passwords API. That API is completely free to use, and I encourage everyone to do that. It's very useful for a lot of purposes. So currently, there are, I think, 903 data breaches that we have already loaded. And that number, unfortunately, keeps on increasing and will probably keep on increasing. We have over 15 billion accounts in the database. Of course, an email address can be associated with more than one data breach, in which case it'll count as more than one address, but there are over 6 billion unique email addresses in the database. So doing the maths, pretty much every email address in there has been breached at least twice, up to 3 times, and many email addresses have been breached many, many times before that. And also just the breaches that we know about and uploaded. There are over 1 billion password hashes in there. And I say password hashes because the Pwned Passwords API does not store the actual password. We just store SHA-1 hashes of the passwords for people to be able to look them up to see if the password they are using is not safe to use anymore. That's the purpose of that service. The team consists of 3 people. Troy, founder and CEO, created the service. Then there's Charlotte, his wife, who actually used to be part of the NDC crew. Awesome person, as well as the rest of the NDC crew. And then there's me, first employee. Charlotte takes care of sort of the operating business side of things, and Troy and me do a lot of development work. Now the reason we have 17 billion requests going into the service is because we have a lot of integrations. This one is actually my favorite because I actually made that one. It's sort of how me and Troy got to know each other about 7 years ago. I used to work for CCP Games, who do even line, and I integrated with the Pwned Passwords API to let our users know if they had a weak password. So when they were logging into the service, we were actually able to check the password hash. Is the password, has it been breached? And then we can notify the user saying, hey, like the password you're using is not safe to use anymore. Another one is Watchtower. This is part of 1Password, which is a password manager. I highly recommend everyone uses a password manager. In this case, 1Password has a feature called Watchtower. I'm pretty sure it's disabled by default, but you can enable it. And it will regularly check with our APIs in a safe manner, and it will let you know if any of the accounts that you have in your password manager or passwords either have been breached or are not safe to use anymore. So it'll tell you about it beforehand. Then Mozilla has what they call Firefox Monitor. That's a very similar service. You can register your accounts in there. I can't remember if it hooks up into the built-in password manager, but you can at least register email addresses, and it will also notify you if you are in a data breach, and all of these services use Have I Been Pwned APIs behind the scenes. Talking about traffic. This is the trajectory we seem to be on. I basically just added that last column this morning. And it seems to be like growing exponentially, which is good, but has its problems, which is sort of the reason for this talk. And this is what a typical month looks like. So these are the last 30 days. You can see they have been found as the website itself, 6 million unique users, almost 1 billion requests. A lot of data goes through, and the Pwned Passwords one is the biggest one by far. 430 terabytes served, 16.4 billion requests. And the issue with serving all these requests is it's a lot of them, but the numbers, when they get so big, they kind of don't register how big they are. To put it into perspective, 17 billion requests is 6,500 requests per second on average. That's, imagine your server is taking 6,500 requests per second, 24/7, 365, all the time. Like I said, 6 million unique visitors, hundreds of terabytes. And this tends to add up pretty quickly. Most of our services run in Azure, for example, and if you're running a small website in Azure, you get like provision. There's a lot of data transfer that's free, but once you exceed a certain limit, they start charging you for the egress bandwidth. Egress bandwidth being the amount of data that goes out of the Azure data center and to your customers. So I decided to take 430 terabytes, put that into the calculator, and it came back with this number. And that's just the bandwidth. So obviously, a service run by 2 people would not be very sustainable if this was our monthly bill just for the data transfer. So like, fortunately, we really don't have to pay this amount of money. But the stack we're using helps us a lot. We use Cloudflare extensively. We have Cloudflare Workers, which we use for edge processing. We have their CDN, which we use for caching, as you'll see later. And then we have what they call Turnstile. And that's an anti-automation thing. It's the typical thing where you're like logging into a form. If it thinks you might be a bot, you have to like click a little checkbox, and it goes on. If it doesn't think you're a bot, like nothing happens. Azure, the biggest part of our stack. We use Azure Web Apps. That's the website. Functions for our backend APIs. We use Azure Container Apps. We use that, for example, we have a small Redis instance that we just use for caching. We have OTel collectors for telemetry. And one of the biggest things we have is Azure SQL HyperScale. That's where most of the data lives today. But we also use Azure Storage. That's where we store our hash ranges. I'll get into that in a bit as well. We use Azure Blobs, tables, and a few queues for some background processing. So let's get to the first issue that we had, or the first thing we have to look at, which is the Pwned Passwords API. So like we know, there are only two hard problems in computer science: cache invalidation, naming things on off-by-one errors. If we take a look at how the API works, it's really simple. Let's use Hunter-2. Does anyone know what the Hunter-2 reference is? Few people. All right. So if we take Hunter-2 and we get the SHA-1 hash for that string, it gives us this hex string, which is 40 characters long. And to use the API, we basically take the first 5 characters. We split it up into a prefix and suffix, prefix being the first 5 characters. And we do an HTTP request, api.pwnedpasswords.com/range, and the first 5 characters. The reason we only send the first 5 characters is we are utilizing a method, a method called k-anonymity. So because if we would send the entire hash, we could theoretically know which password you're looking for, even if it's been hashed, because hashes being very deterministic, the same password will always get the same hash. So if we have seen that hash before, we might know which password you're searching, so we don't get the entire hash. You just get like first 5 characters, and we will give you back a list. That list contains all the possible suffixes for that prefix, and if you find the suffix in there, then you know that this password has been breached. In this case, the password Hunter-2 has been at least seen in data breaches that we know of over 27,000 times, which might indicate that it's not a very good password to use. So that's all there is to the Pwned Passwords API. Because of how Have I Been Pwned works, we load data breaches, and after we've loaded them, the data is pretty much static. And when you have a lot of static data, you can do CDNs. CDNs are absolutely perfect for static data. And that's why we went with Cloudflare. They have 330 edge nodes currently, and I don't know if you can see that, but like in the bottom right corner, 95% of the internet connected population in the world is within 50 milliseconds of the nearest Cloudflare data center. So that's what they're aiming to be, the 95th percentile of the response times, which is fast. To put it into perspective, 50 milliseconds is faster than you blink. So Cloudflare caches almost all of our static data. They have, and we utilize what they call the tiered edge caching. So basically, they have a cache on each worker node. If you're looking for a resource that's not on that node, they check the nearest neighbor node, and hopefully they find it there. If they don't find it there, they go back to the origin. So by using this, our origin is spared for most of the data, and the added benefit of this is that it brings our data closer to our users as the cache gets populated. The beautiful thing about Cloudflare is that not only were they caching the small parts, but for Pwned Passwords, we used to have, like, you would be able to download the entire hashes that we have, because you can access all of these hashes. We used to put them all in one big file. It was like multi-gigs file. It was like 12 gigabytes or something. And they even cached those as well, which was awesome. But every time everything is awesome, they tend to not be awesome at some point. So, January 2022, Troy gets his Azure bill, and it goes a little bit like this. The reason it went like this is what the bill looked like. So up until December 20th, 2022, everything is fine. But then something happens, and the bill just absolutely skyrockets. I blame these people for that. I technically don't blame them. They do play a very small part in it, but it's not because they did something wrong. It's because we actually decided to start working with them. So we open sourced the Pwned Passwords part of the API, and you can see the date there, December 20th, 2021. And as part of open sourcing it, we both gave law enforcement like FBI and the NCA. They have NCA, for those that don't know, sort of like the equivalent of the FBI, but in the UK. We gave them a way to ingest passwords, because they do a lot of investigations. They investigate cybercrime. they often get their hands on credentials, and this was a way for them to get the password part of the credentials to us, so we could notify people that their password was no longer safe to use. And they did that because the service is completely free. As part of that, we added 225 million new passwords. Now that was a sizable increase, and it actually turns out that there are limits to how big a single item in the cache can be. So these multi-gig downloads that I talked about before, we blew their limit. They exceeded 15 gigabytes. Cloudflare said, nope, we're not going to cache this anymore, it's too big. So all the traffic went to our origin servers. And because it wasn't a lot of traffic, it was just, sorry, it wasn't high throughput, but it was a lot of traffic. So we didn't even notice because there wasn't any, it didn't exceed any CPU usage or anything on our workers. They just kept running, but they were just serving a lot of data. So that means that we couldn't serve those big files anymore. So the fix that we needed to do was, okay, we need to fetch the individual hashes then and then combine it into one big file for the user. So we created a downloader. And you can actually just use the downloader if you want. Download it, install it as a tool, execute it, and it will download all the hashes, put it into one big file. So that fixed the 15 gig issue. So instead of one big file, we just have a downloader that in parallel goes and downloads all the individual smaller files. And those are all cached. A year later, we decided to make another feature upgrade to the Pwned Passwords, and we add NTLM support. NTLM is another form of hash. It's used, for example, in Active Directory, where you can export users' passwords in Active Directory to NTLM. So Active Directory administrators can actually look over the hashes without knowing what the passwords are and notify people if their passwords are not safe, even without knowing what they are. And then twice slides into my DMs again, and we start seeing these spikes in the egress data again. This is a year later. So we were had been on the fence about this and then created alerts, so we actually knew about this beforehand. And we start looking at why this is happening, and now we have new cache issues. Items that we put in the cache and had Cloudflare caching were getting evicted a lot more frequently, which makes sense because when we added the NTLM hashes, we pretty much doubled the key space, as well as almost doubled the amount of storage we were using in the cache. Even if it were smaller files, we just had a lot more smaller files. So the cache hit rate started dropping. When the cache hit rates drop, our bills go up. So like I mentioned the tier caching Cloudflare has. And this is pretty much what it looks like. You have the client, you have the origin. It goes to the edge cache. First one, doesn't find it, goes to the next one. If it fails there, it goes to the origin. And this is what we were seeing in increasing numbers. So we got back to Cloudflare and said, is there something that we can do about this? And it turns out Cloudflare actually has a product exactly for this scenario, which was the magic that's inserted over there. And it's called the Cloudflare Cache Reserve. So you can think of the cache reserve as a cache for the cache, and to be completely go over the top in puns intended, to spend less cash. You can think of it as like an R2, Cloudflare calls it R2. It's pretty much the equivalent of S3. You think of it as an S3 bucket behind the cache. So whenever you cache thing in Cloudflare, if you have a cache reserve enabled, it will put a copy of that cache basically as a just file blob in a blob storage. And because it's a blob storage, it doesn't need any memory on the servers. It will actually look in there. So it's a feature you have to buy. It costs a little bit more, but it's a lot less expensive than having the traffic hit your origin. So this took our cache hit ratio from hovering around the 98 to 99% up to 99.9999, and that is actually not a number I just pulled out of thin air. We actually did the math, so it's literally, once we've populated the cache, like 1 in every million requests hit our origin, which is almost nothing. So that brings us to another issue, the big SQL migration. I saw this quote somewhere and I liked it, so I decided to add it in there. Our backup strategy is bulletproof. The bullets just move faster than the backups. All of the breach data that we had before the migration was stored in Azure tables or blobs as well. We sometimes use blobs as a caching mechanism. Super fast. It hardly matters how much traffic we put toward Azure tables. They usually just handle it with little latency, so it scales absolutely beautifully. Backup strategy is very easy. You have a tool called the AZ copy. Just download everything, just point it at a table, download to a JSON file. If you want on your store, just create a new Azure table, upload the file again, and voila, you have all your data back in. That's simple. Table design was simple. 2 tables. For standard email lookups, if you've ever used Azure Table Storage, you know that it consists of partition and row keys. It's sort of how the data is sharded within the Azure table. We put the domain as a partition key, and the email alias, that is everything before the @sign, as the row key. So if we were looking for like a specific email, it was super fast, and if we needed to get all the emails for a domain, we just fetched the entire partition and got that back. So it was a very handy mechanism to store this, very cheap and very fast. Then there's just an added column that just contained like a semicolon separated list of breaches. We had another table which was used for hash lookups. And like you saw with the prefixes for the passwords, we do a very similar thing with emails. So we take a hash of the email and we use that as a lookup mechanism to fetch groups of emails. So we had the hash prefix as a partition key, suffix as a row key, and again, just a semicolon separate list of breaches. But I told you at the start that these tables only contained around 6 billion rows each. And if you want to imagine how long it takes to download 6 billion rows into a JSON file, it's about this. And I'd like to make a note that this is us running in a VM in the same data center as the table storage. This is not us like going overseas and fetching it. This is like right next to it. And obviously this is not sustainable if you want to have a solid backup strategy. If anything happened and we had to spin up another table instance, we basically have to say like, sorry, we're down for a week, we're getting everything back up while we upload AC copy, and then hoping that the AC copy wouldn't fail. So we decided that we would go with Azure SQL. There was already an Azure SQL database used for like a lot of the metadata, like the list of breaches, the subscribers, and everything else. But with the amount of data that we were going to put in there, we needed it to be efficient. We don't have any downtime, so we need to be able to, when we have a big data breach, insert millions of rows without taking everything down. Because this data is getting queried all the time as well. So we're both very proficient at SQL, but we're not experts, so we got some help. And I would like to use the opportunity to give a shout out to these 2 people who helped us a lot. We decided that we would just keep it simple. I don't know if you can see this, but I'll just go over it really quickly. We created a table for the emails, just contained like a 64-integer primary key, the alias, domain ID, which is an integer because we store the domains uniquely in another table. We have a 3-byte binary column for the prefix, and then just a couple of bit columns for when people are opting out and don't want their data loaded. So we have to be able to know if that's the case. Then to connect all of this, of course, to the breaches, we just have a small table that contains the email ID and the breach ID. And that's just what maps an email address to a data breach. This table we decided to just use like a composite primary key. And doing all of this, or designing these tables, they look simple, but I can't tell you how many iterations we went through to make sure that this was running and performing as we expected, like doing all sorts of different things. So there are some tips we learned along the way. If you have composite primary keys, make sure the most specific one is the first one. Because otherwise that's the one that the index is going to be ordered after. So you want the most specific one to be first. Table and index compression. This is like, I've worked with SQL databases a long time and I've been a SQL admin. But it makes sense when you think about it that they suggested that we use compression. The reason being that usually the CPU on the server is not the issue with your database. Usually it's the amount of data that you can push through it, either like I/O limits or something else. So if you're storing the data compressed, it means that you are reading a lot less data and saving it as well. It just gets compressed and decompressed on the fly. And CPUs usually handle it a lot better than the disks can handle all the data that you're loading back and forth. So table and index compression was something that worked really, really well. Another thing that we eventually found out that we needed to look at was index fill factor and padding. It basically means that when you're creating indexes or putting data into the table, it basically tells the database to like keep some extra space because I might be inserting data in there later. Because the data we are inserting is not, we don't append it to the end of the file. It goes like randomly into the tables, and we tried to figure out a way to get around that, but we couldn't really think of a practical way to do it without bloating our data sizes considerably. So we ended up with going with a fill factor, which pads them, and that leaves space for the inserted rows, so we can actually insert a bunch of data without impacting the database too much. So once we'd done all this, we'd done a bunch of testing, we decided that we were going to roll things over. And much to our surprise, it pretty much all worked. And since we were now in a scenario where everything was working fine, running against a SQL database, we could spend time on optimizing things. And I don't know if you've heard of SP Blitz. Has anyone heard of this for SQL Server? So Brent Dosar is like, he's a SQL Server guru. He's been working with SQL Server databases for, I think you can say decades now. This is basically all of his knowledge and experience put into a stored procedure that you can run, and it will give you basically a list of actionable items that you can take a look at. And usually this is things that he has, through his experience, seen are going to be problems within SQL Server. So I recommend you take a look at that if you're working with a SQL Server. So that brings us to the next big issue that you had. I love parallel programming. Nothing beats doing twice the work in half the time, except when it's doing half the work in twice the time. So Azure SQL HyperScale is a bit different than the normal Azure SQL Server. It takes the processing and it shards it up in this thing called workers. It's like a different query processor for the queries that have to can run in parallel. You can do a lot of things in parallel as well. You can almost like if you work with the .NET thread pool, you can almost think of workers like threads in the .NET thread pool. It's a similar thing. HyperScale can scale to a lot of them. I mean, you have this thing on HyperScale server called the vCore. The max vCore count is basically how many cores you're allocating to the Azure SQL database. And as you increase it, you are basically behind the scenes getting more machines. You get more RAM, you get more workers, you get a lot of things as the core count increases. And parallel queries are awesome. There is a thing in SQL Server as well, which is good to take note of. There's a setting, server-wide setting called max DOP, max degree of parallelism, which controls, like if you have a query that's fetching a lot of data and it can do it in parallel, this setting will limit the server saying like, even if you could do like fetch 20 things in parallel, just fetch like 8 of them. Don't do any more because you don't want to eat up all the CPU like with a heavy query. So it's a very good setting to keep track of. One of the things we got out of running SP Blitz was, and one of the top items it actually mentioned to us was that, and this is one of the quirks in SQL Server, and I was actually surprised when I saw this. If you create like a user table valued function in SQL Server and you use it in a constraint on a table, there will be, SQL Server will fall back to serial execution every time you do anything with a table. So if you put that constraint on a column, even if you're not selecting that column, the query that touches that table will never ever go parallel, which is not good. In our case, the domain table actually used a function like this when we were inserting data in domains to make sure that the domain was valid, like it didn't contain like a period at the end, that it had to contain one period, etc. Just like a very simple validation function. So since we already did that check when we're processing breaches, we thought, okay, we can just remove it. That'll allow the queries to go parallel, and everything will be fine. We did that, and everything was fine, until I went on vacation with my family to a cabin, and Troy starts calling me. Pretty much the only time he has actually called me, and thankfully I did have my laptop with me, even if I was on vacation. And this is what we're looking at. So this is, to put it like very simply, this is like one query we're looking at in the Azure portal. And we're looking at the query over a 24-hour period of time. And that, like the bottom charts, that's how many times the query was executed. And everything is fine up until like the last hour. And then like everything goes haywire. CPU starts spiking. And even if we're looking at 24 hours, the total execution time for the query was almost approaching 3 days. Of course, you have many cores, so like the time adds up. And even if the query was being executed a bunch of times, it was fine for the most part until that last hour. Then everything went nuts. And we start looking into what actually happened. So I talked about max DOP. When you create an Azure SQL database, and that's the experience Microsoft has, they've looked at like a bunch of telemetry. They have a default value of 8, which is it's a sane value. It's a very good value to have. So basically, if a query can go parallel, it will only like split up to 8 threads. So this, pretty much, the parallel queries are awesome, turned into this. It's not awesome anymore when the query starts running without any limits, and it's the query that gets executed most on your server. Now, the no limits part is actually what confused us, because we'd looked at the documentation, and it didn't make any sense. Like, why is it eating up all the workers and CPU on the machine when we do have a limit in place? And that's when I noticed this. This is a note on Microsoft's documentation, and it has this bit at the end. So they did not change the default value for databases created prior to September 2020. Remember, the service is created 2013. And as you can see right next to it, the max DOP value is 0. Some might think 0 means never go parallel. That's not what it means. It means you can go as parallel as you want. And we found that out the hard way. I started reading the blog when they actually announced this, and I wanted to thank Microsoft for gaslighting me, because they put in this sentence there at the end. So like a subtle, it's a subtle RTFM thing they put in there. So yeah, we figured out that the max DOP was 0. We changed that, fixed the issue. No more issues with the parallel SQLs. But I've been talking about HyperScale, so let's talk about autoscaling Azure SQL HyperScale. Autoscaling is great. I just autoscaled my budget to 0. HyperScale scales, obviously. It's sort of what you can take from the name being in there. And I mentioned the vCores that they have. So you have a value that you can configure called max vCores. And that's the maximum amount of cores you are allowed to use. But you only pay for what you use. So you can set the max vCores to a high level. And if you're just using a part of them, that's the only thing you're going to be paying for. Now there are, because you take different amount of cores, they do like the lower limit actually increases as the higher limit goes up, but there's still like a sizable gap. When we're processing and loading the big data breaches, we just take it to the maximum, because we know we're just going to take it to the maximum for a short period of time. And we keep it there for a little bit, because after we load a data breach, we need to flush the cache. That brings all the traffic to our servers. So we just keep the DB at 80 cores while most of the traffic goes away. And this is what it looks like in the Azure portal. You get this nice slider for max vCores. The minimum vCores goes as well. In this case, you can see we can go up to 80, which gives us 240 gigabytes of memory, which is awesome. And even at 4 cores, you have 12 gigabytes of memory. So it's a very simple action to scale the HyperScale database up and down. Now, this is also taken from Microsoft documentation page as an example of how you would be billed for the vCore. You might set the max at 4, the minimum at 1, and the orange part is the cores you're actually using, and like the green bits are what you're going to get billed for. In this case, they actually show an example of if you don't get any traffic, you can have it automatically pause your database. That never happens for us, so ignore that part. But it shows you that you would always be billed for the minimum amount of cores, but if you're between the minimum and the max, you should only be billed for what you use. So as traffic trickled down, our core utilization goes down as well. So we should be paying less. And this is what our utilization normally looks like. You can see it. There's a big spike at the start, and that's usually after we flush the cache. Then slowly it starts to just flatline out, and usually hovers around the 15 to 20% on that area. So we figured, all right, if we would be running at, looking at the chart, so we would be running at like 15, 20%, we should be like at the lower limit there, and not be paying for the maximum. Of course, that's not how things tend to actually work in real life. We did things, configure max, hoping we'll not be billed for the maximum except when we're using it. And this is one example that we did. We were looking at a 40-core instance. That's actually when we were looking at the issue. It was in the low 20% ranges. Billing expectation was 4 to 8 cores, but we're getting billed for all of them, all the time. So we start reading through the documentation once again, like trying to figure out why this is. I mean, we're looking at the CPU, we're looking at different CPU charts, and every one of them says the same, like we're not using all the cores. And then I find this bit. And this is not even in a note. This is like at the end of a text paragraph, somewhere in the documentation. It basically says like, the amount billed is the vCore unit price times the maximum of either like the minimum cores used, but then they throw the memory in there. The minimum memory, but they're nice, they only say like 1/3 of it, or the maximum 1/3. And this is the bit that actually bites us. The reason it bites us is because this is the memory we're using on the SQL Server at all time. This is looking over a 30-day period, and it is just almost flat at 80%. There are tiny dips and tiny tops in there. Those are scaling events when we're scaling up and down, so we get a little bit more memory or a little less memory, but it just keeps flat at 80%. The reason it keeps flat at 80% makes perfect sense when you think about it, because that's how SQL Server works. SQL Server is built to acquire as much memory as it needs without creating a memory shortage on the system. And it makes perfect sense because you would like your data to be cached in the memory instead of SQL Server always having to go to disk to fetch your data. But in our case, our database is so big that it won't fit into memory. Like if you're running a SQL Server HyperScale database and you have 12 gigs of RAM and your entire database is only 1 gig, the max vCore and min vCore is going to work perfectly fine because you're not using all that memory. In our case, our database is a little over 1 terabyte in size, so we are always going to blow the memory limit. So we go from scaling to autoscaling. We actually figured out that you can configure the max vCore count with a SQL statement. You can execute a piece of SQL, and it will scale the database up and down. And that was a bit of an eye-opener. So we decided to write our own autoscaler. As most Microsoft products, or at least SQL Server and their server products do, they have a ton of performance counters behind the scenes. So we can actually write queries and look over a time window and see like how much CPU is the database using, how many workers is it using, etc. So we created a proc that basically gets called every minute. It looks at a time window, and if our CPU or worker usage is above a certain threshold, we will scale up. If it's below, we will scale down. And to prevent us from like falling into an oscillating loop, we suspend all scaling events for 10 minutes after we've either scaled up or down. And that's just to give the system time to stabilize, because obviously if you think about it, when you scale down, you might be tearing down a server. Every app connected to the server is going to lose its connection. It's going to have to reconnect, and it's going to cause a lot of thrashing. So that's why we wait for 10 minutes after scale events to actually start looking at data again. And this, remarkably, just works like a charm. This is a typical graph. I actually took it. This is just like from the last 30 days. In the middle of August, we loaded a very big data breach. It did a lot of stuff. That's why our core count went up to 80. And then we turn on auto-scaling, and you just see it like slowly trickle down. Then we load a smaller data breach, goes back up, slowly trickles down again. And this is saving us a ton of money because we can't count on the max vCore or min vCore is actually doing for us what it should be doing. Brings us to our next thing, edge processing. So we have edge processing. We're using Cloudflare, and Cloudflare has Cloudflare workers. So after we moved over to a SQL database, it made us a little bit more, how would I say, like susceptible to like traffic spikes and things like that. So to be careful of how we utilize our DB, we thought, okay, maybe we can just like maximize what we have and move a lot of the processing from functions that are always calling a database and just move it towards the edge. So when we do have like big breach loads and we have to purge the cache, that's inevitably going to cause load in our database. But sometimes we have periods of high interest. Let's just say there's a very high profile data breach. A lot of people are going to the website looking at their address, and then we get a lot of traffic. So we decided to move processing where possible. We had a lot of processing in Azure Functions where that has worked very well. They were just querying the database, returning data back in the back end, and that was being looked up. We decided to move that over to Cloudflare workers. And the way we did that is very similar, like I showed you with the passwords. We have a similar internal endpoint that gets emails based on hashes. So we batch them up, so there's just a limited amount of possible queries that we can make, and we can actually cache those on the Cloudflare end. And again, the data is now geographically closer to where our end users are. So before we move to workers, if a user in Europe decided to search for an email address, his browser would do a client-side request. That request would eventually go to a function in the West US. So that's a round trip of at least 300 milliseconds. The function would create the hash of the email. It would do the hash lookup. If it finds it, it would do the same thing, return the data. So it went from the browser to the function to the database and back again. So going from Europe to West US, it's a big latency, and it's even bigger if you as further as you go. After we added the workers, there's no difference in experience for the user. However, the request now goes to a Cloudflare worker, and as I said, the nearest node is most likely within 50 milliseconds of you. And with the amount of traffic we get, in all likelihood, that node is going to have the data that it wants already cached. It's going to create the SHA-1 hash of the email. It's simple. If it's not in the worker cache, it will go to the function to fetch the prefix, but that will only happen the first time. After that, the data will be cached. And since we're fetching prefixes, if you search for an email that's not in the cache, you're actually loading the cache with a lot more emails, not just the one you were looking for. So eventually, as the requests pile up, we will be caching most of the data that we have. It will search for the entry, return the results. So in the worst case scenario, it'll go from the browser to the worker. It will go to the function in the DB, but only once. After that, this part just goes away. So no traffic hits our origin servers, and the user will probably get his response in less than 50 milliseconds. So the benefits that we have is the difference between the password, for example, the email hashes, is we use 6 characters. So instead of being just over 1 million possibilities, it's just over 60 million possibilities. So it's still a finite number of URLs that can possibly be fetched, and that can therefore be cached. Each prefix only gets hit once by our DB after we purge the cache. Usually, after we purge the cache, we see that it takes about 2-3 days until most of the data has been cached on the Cloudflare edge. Super fast results to our users. And again, like I mentioned, the cache reserve before, that comes into play there again and helps us save a lot of the data. But how fast is too fast? Can you go too fast? Turns out you can. After we did all this, we deployed a new version of the website. We cleaned up a bunch of client-side code. So it actually became almost too fast. This is looking for a password. The result is instant. After you click the button, it changes it. Result is instant again and again. And when we were actually looking at it, we were looking like, oh wow, this is awesome, this is instant. But then the thing clicked in our head with like, this looks artificial. It almost looks like we're just generating a random number, putting it out there, but we're actually not doing that. So in this case, the user experience actually suffered because we were returning the results too fast. Now, we didn't want to slow things down, but to put things into perspective, like I said, we're hitting Cloudflare worker nodes, and this is the time it took to get the data. This is from like client machine, going to a Cloudflare Edge node, getting the results back. Like I said, it's under 50 milliseconds. And a browser, like if you have a like proper machine, it doesn't take it long to actually render the results. So to fix this, we didn't actually slow anything down. We just, instead of having things blinking when people were like putting in the passwords or searching for something, we just put in like nice color transitions or animations, like really subtle. But it sort of fixed the issue that it didn't look fake anymore. Then we get to monitoring and alerting. Said monitoring tells you what's broken, alerting tells you when you broke it, observability tells you why you'll never sleep again. If you've ever worked with like a really big system and you integrate something like OpenTelemetry and you start seeing the actual traces, what the system is doing, have you ever had that, oh my God moment, what is it doing? Like why is it making 52 database requests for something that should be that simple? That's usually what you get the first time you start looking into this, if the system's big enough. Azure Apps and Services expose a lot of metrics. This is one of the things that Microsoft is actually very good at. If you're running an Azure app or a web app or anything, even if it's running on .NET, you get even more. Like you get the requests, you get result codes, you get timings, you get how many requests are in the queue. You can look at garbage collector statistics, and like the list is pretty much endless. We take all that data, we push it into a log analytics workspace, which makes it possible for us to query this data and put it up into dashboards and other nice things. So we use that a lot. We have alerts, for example. We look at CPU usage on our web app. If it exceeds a certain threshold, we trigger alerts. The alerts can do anything from like sending an email, can even call your phone, or you can trigger external services like PagerDuty or whatever if you have. We're currently working on migrating a lot of this data over to OpenTelemetry. If you haven't looked at OpenTelemetry, I highly recommend it. It is finally that like we decided to come up with a standardized way of doing traces and metrics and logs and all those things. And that's what OpenTelemetry is. So I definitely recommend you check that out. We use Grafana a lot. We use that to visualize our metrics. We use it to visualize both metrics, alerts, and basically just for general querying if you're looking at an issue, create dashboards as well. And this is one of my absolute favorite tools. It's Observer. Has anyone heard of this tool? Pretty sure not many people have. It's a pretty specialized tool. It's created by Stack Exchange, and it's sort of their internal monitoring tool, which they decided to open source. It's very much geared toward their stack, but it has absolutely awesome SQL Server troubleshooting things in it. It can watch Redis clusters as well, which is great, and a bunch of other features we're not using. Azure Monitor, like I said, you can look at metrics, you can create your custom alerts, custom queries. They exceed a certain threshold, either like below them or above them. You can trigger alerts as you see fit. Grafana, awesome for looking at things at a glance. We have dashboards, for example, in this case, we're looking at our database. We see the CPU usage. We see how many connections it's doing, memory, how many, like what's the core count and everything else. Observer, again, my favorite. You probably can't see much on this, but if I tell a little bit what's on there, like this is looking at our SQL Server. We see things like how many transactions is it doing per second, how many locks is it taking, how many queries in the query plan, how many of them are cached, etc. There's a ton of data that you can get all this data by running queries, but having it in a visualized way is really, really nice. It also has this view of like currently executing queries. So if you have a query that's taking really long, then we can pretty much just open up Observer and it will tell us why it's taking so long, usually. If it's waiting for a lock or if it's in a deadlock, we will see that in there. You can see the query, how long it's been running, how many CPUs it's been using or reads, etc. And it can even give you like the high score of your queries. Like these are the queries taking up most time in the database since your database was restarted. For example, in our case, we can see a query that's usually being executed like over 320 times per minute. And since the server was last restarted, it has taken up a total of 24 minutes of CPU. And when you actually click the query, you can even get the query plans. So if we have an issue, for example, with a database query, the first thing I do is I open up Observer, I find the query, and I can look at the query plan, and I almost immediately see why is it being so slow. And it also gives us a good view into what we should be optimizing. So I highly recommend you look at this tool if you haven't. So just a small recap. When you're scaling and you have to think about scaling, there are several things you need to think about. Like, first of all, like, do you have the headroom that you need? Like, do you need to scale at all? Like, maybe your headroom is that big that you don't need to think about it. But there are other things to think about. For example, if your cache breaks, what's going to happen? Are you running your service so tight that if the cache breaks, like everything will hit the floor? If you're lucky enough to, like, for example, your service becomes very popular and you get a lot of traffic, will it be able to handle it? Like, do you have the infrastructure in place to either scale it up, or will it just be able to handle the traffic that you get? Like in our case, fixing things can actually sometimes make things worse. It sounds weird, but it's the classic case of I fixed one bug and now I have 2 bugs. Because the other bugs we didn't see until we fixed the first one. So I'm not saying it's bad to fix things, but be aware that you might be exposing yourself to other bugs that you weren't exposed to because the other bug was hiding them. And the big part, sort of the takeaway from all this, is observability. And this is sort of my personal opinion on this. If you don't know what is happening in your system, you're always going to be reactive instead of proactive. So if you're, like dashboards, for example, are a good example. Dashboards can show you what's happening or what happened, but it's not going to tell you what's going to happen. What you want to be is you want to be in the situation that you're able to tell, like, okay, every time my web server CPU hits 30%, I know I'm going to get failures. So what you should then be looking out for is like, okay, the last 10 minutes, has my CPU usage been increasing? And you can create alerts saying, like, your service is going to hit the floor in 10 minutes if you don't do something. You'd much rather want to be in that position than having to deal with the fallout afterwards. And observability is absolutely the best place to get there. So that's it for me. Thank you very much. Hope you enjoy the rest of NDC. I have a bunch of stickers here up front if you want to come and grab them. Thank you very much.